Hello, I'm Rasmus Jørgensen, and I'm trying to give this screencast. Michael Søndergaard Nørrebo Madsen will give, that's within 1 or 2 hours. He is within machine learning, a machine learning expert, whereas I am an agronomist. So that's me. So I'm senior researcher here at Aarhus University, Department of Electrical and Computer Engineering. So I've been working with computer vision for detecting weeds and crop for many years and automation. Let's get back to the presentation. So the talk here is how we are investigating how we can enhance the precision weeding using YOLO object tracking. That's a new state-of-the-art for robust early crop detection. And that's because we in the spring will do spraying. So just to show the case, this is FarmDroid, who was so kind to let us collect images with the camera here for every 10 centimeters. The flash is so fast so you won't see it in the video. And then the idea with tracking is, here you can see how it works. You can see the line or the trace. The yellow ones are sugar beets, the blue ones are dicots, and the red ones are monocots. So you can see that, and the green lines, punctuated lines, are where the model think there is a row based on 3-meter history. So the tracking here is what we really want to investigate, because we thought that would be cool. That could potentially increase our accuracy in how we classify objects. So that's the core idea of this presentation. The other author, Søren Kelstrup Skovsen, is a postdoc, and he has done a lot with supporting getting the model up running, which is doing this with segmentation and detecting objects, whereas Michael, he has worked a lot on the tracking part. Bo Melander is the leader of this work package, where I'm just the agronomist who wants this to work. So we will claim here that this is a game change of conventional and organic farming. And what we will show is that YOLOV11 with tracking, it improves the early sugar beet detection with almost 9%. So it's a quality. It also reduces misclassifications and make it more consistent in what we're doing. And of course, the aim is here for us is to do organic precision spraying, but we'll also try with glyphosate. But as you saw, FarmDroid was the host, and FarmDroid has a product here where they do micro spraying. And when they do that, they can they only use 6% of the herbicides compared to blanket spraying. So that's really a decrease in herbicide usage. The problem, however, is that the earlier you can spray, the better the herbicide will work, but the more, let's say, the crops don't like to be sprayed, so they also want only to spray where it's needed. So, for example, where there is weed. Currently, the system is blind, so it will spray all sugar beets and all areas where sugar beets have not emerged, for example. It's better, definitely, than just blanket spraying. But they also have an interest in could vision improve this. That's probably also why they have accepted hosting our little game here. Now Michael is presenting, and yesterday he noticed there was some confusing about the concepts when he looked at it from the machine learning part. So here I will do my best as an agronomist, but you have to discriminate. You have object detection, which is kind of, you find the object, put a bounding box, and then you classify it, or sugar beet, dicot wheat, and there is a trace because it's assumed from a monocot. And that is YOLOV3, 5, 8, 11. But the next step is where Søren Skovsen, that's what YOLO V8 segment and 11, and you have mask RCNNs. That's where you create a pixel mask around the objects. So that's even better and more complex. And what we are looking into here is to take the next step to use the object tracking to follow it across multiple images. And there's byte track and deep sort as kind of the add-on. So just to summarize, object detection is just the bounding boxes. Instant detection is bounding boxes and mask. And then the tracking is all on top. But we also put an ID number, as you see here, across frames. So we track it. So we get this trace. And here you have an example of how hard it can be to recognize sugar beets. Of course, here it's easy, here it's easy. This one is more difficult. And then you have this tiny one. We could try to zoom to this one. This little one is hard. And it's only because we have so many pixels per millimeter. I think it's more than 6, almost 7 pixels per millimeter. And these ones down here, they look similar to that, except for the reddish. But you can also find these, what's that called? Polar. I can't remember the English name now. But these weeds sometimes look a lot like this one, the sugar beet. In fact, this is one of the images we use to do the assessment. So you can see there's been drawing here. We are using the RoboWeedMap service and their model, which is a lot better than one we are using here. I'll come into why we are not using the top of the best model we have, whereas we are using one which is not trained as so much data. The main reason is we want to assess tracking and not the model itself. So we want to challenge the detection model. And the way we done that is it's split into areas of treatment A. It's this one where there's been mechanically weeded by the robot, and then it has weeded between the crop, and there's one row which has not been weeded between the crop. You can also see there's a big dicot here. There's a lot of grass. And then we have this one, which is in fact not weeded at all, but it's seeded at the same time as this one. See, size is similar. And then we have a late sowing without any cleaning, where you can see that the image you just saw. So we tried really to challenge the model. It's also in the autumn, so the sugar beets are not that happy with the situation. So now you have an idea of the layout. Yeah, the red ones are models which the model, or images which the model has been trained on. And then for the assessment, we will, how well the tracking and the model is working, that's a yellow one, where we ensure that they are not too close to one of the training images. That's the best we can do. So if we just, here's, you can see all the images collected for every 10 centimeters. The GPS we use is not as good as the one the robot used, the FarmDroid. So it's not perfect aligned compared to how the robot. But you can see here the yellow one is sugar beets and the red ones are grass. So it's quite clear that this is a lot cleaner than this one. And here the yellow ones are tiny. So that's the small sugar beets. So it's well aligned with what you see here. And of course it's a lot of objects. So if we just take all the objects and figure out where they are, it looks something like this. So this is cleaner, very dirty and big weeds. And this is late sowing, so it's smaller. So it's quite kind of cool we can do this too. Let's have a look at it. So if you take all the bounding boxes you saw and just overlay them. So this one will probably be here. This one, when it moves down, it will be seen 5 times. But if you just take all the position of the center bounding box and then create a heat map for each treatment, then you will see, and this is for dicot weeds, so it's these ones and these ones. Here where there's no weeding, it's kind of nice to see that there's not really any pattern in it either when we do summing across the 4 rows or when we sum the other direction. It's kind of even distribution. Whereas up here where you had the inter-row weeding mechanically, the density is lower. And down here you can see that there is some peaks here, so it kind of, and that's where the beets are small. You get the suspicion that some of the sugar beets perhaps are not classified as sugar beet, but as dicot weeds. And then of course we have this one, because we had one of the 1, 2, 3 rows where 1, 2, 3, 4, I can't count. One of them, this one, was not weeded, intra-row weeded mechanically. It was disabled, and that shows up nicely here. So we get an idea of that the model is making sense, at least if you look at the main treatments. So that's nice. So let's dive into the sugar beets. If we just use, how should we put it? We don't use the tracking, we just use the model as the classical YOLO model, what you see and then learn and then classify it. Then you get this, and you get an idea if it's more noisy down here. There's some false positives. You still have a clear row structure, and you can see how accurate the robot is driving. You get an impression of that. It's the same across all treatments, all rows, same center or top. But if you then do tracking, and I can flick, you can see there is a reduction. Be aware of that the color, we should have frozen the color bars too, but the counts. So you can see here that there's fewer false positives here, at least. So it seems like tracking, if the object has been seen 4 times, is doing a better job. So tracking of sugar beets visually, if we then take the yellow images, that's not the yellow, the images we selected for assessment, the 233 images, then the performance here, if you just look at it as a standard YOLO model, you can see only 4 out of 10 is classified correctly. That is not good. If we use the best model from the RoboWeedMap service, we would have get not this high, but we would get a lot closer to the 90%, probably 90%. But the aim here was to assess the tracking. So if you do the tracking and we just say this is stupid, and then we use the tracking where it's kind of moving, if you're moving downwards and say now the image we are going to assess is there, then it will use that it has realized there is a row structure, and it will use that some of the objects, especially the one in the bottom, has been seen several times. Just that part shows that we will go from 4 percent points will the improvement be. And if you use at both directions, false positive, false negatives, and all that stuff, it is an increase in the detection of 9%. That's quite significant. These one here are they're hard to explain, and we will have to work on how to explain it. But the idea is that this is kind of, you're moving downwards. Now we have the image, and we do the assessment based on me annotating these 233 images. These ones here are saying we have moved all the way down, so all objects have been detected 5 or 6 times, depending on when they enter the frame and when they leave. So if you use that and then just use the last detection, which because we move, we see it 5 or 6 times, quite a few of them will have been cut, like this one here, partial, just being partial. So that's also harder for the model. So they are not, that's worse than this. And if you take the final track where we just use all detections, then it's not as good as this one. And the reason, here's the room for improvement, which we didn't manage to get up running for today. But the reason is, our best guess is we cut it both when it enters and it leaves the image. So the way we weigh it and reasoning will not improve. If we worked a little with this, we could probably elevate the precision here even more. And that's what we will aim for. But the short story is tracking helps for sure. So now you'll say, yeah, we want to do tracking. Let's go. That's how we said it a month back. A little more than a month, I think. And Michael, he started it up with eager. He's a lot younger than me. But then he realized it is definitely not straightforward just to use the classical YOLO model. Can you see the difference here? What is the difference? You can see here the camera is steady and the objects are moving. Camera is steady, the objects are moving. The same here. What are we doing? We are moving the whole camera. So the whole scene is moving, and we have a low frame rate compared to here. So there is a big translation of all objects, of everything. So let's focus. So we had to do a lot, or Michael had to do a lot handling that. And that is listed here. He had to make a custom cost function. He had to implement the green punctuated line here, the row awareness. So if it's within a certain band, we will, if you just think it's a die cut or a sugar beet and it's within the rows, we will raise the stakes or how much we believe it's a row. And then there was a lot of fighting how to at least maintain the bounding boxes over several steps. But it is possible, but just be aware of it. That's kind of a warning. It is not straightforward if this is the way you're going to use it. So the key takeaways is that for larger sugar beets, of course, the benefits is not as good. The detection accuracy is quite high. This is the big sugar beets. They're also easier to identify. If you look at these as fewer features, that's the late seeded ones, and that's the reason the model has a hard time. It's only trained on approximately 2,500–3,000 images, so, and that's both sugar beet, maize, cereals, buckwheat. So it has seen a lot and not that many sugar beets. So, but it's enough, as I said earlier. So it does improve. The stability also improves. So tracking is beneficial if you just look at performance. And then, of course, we will use it in the coming spring. And here you can see this is a trial made in US by Wesley Moss from Australia. And we can see again, and if you notice, and this is paint, but it could be organic. He has also tested with organic herbicide. And he's able to hit it. We will then mount it with our camera system and this one on the robotic we have at Flakkebeer, and then we will test it in maize and sugar beets in the spring. And we are quite excited to see how that performs. Of course, we will use a better model, a lot better than this top-notch model. But let's see how that goes in the spring. Fingers crossed. And of course, we would like to acknowledge FarmDroid for letting us use their little autumn test field and carry the camera. And the RoboMeatMatch service we used to kind of create the training basis for the model we used here. Their training base is significantly bigger than ours. So of course, we have tested with their model, and that's a lot better than the one we have presented here. We also have access to it via the service. And then, of course, REI, the American project, which is funding all the activities and what we are doing here, and also our participation in this workshop. Yes, that was it. I used a little more than 20 minutes. I hope Michael is faster than me. Thank you.